Okay, it's been a while since I've given you guys an update. I've got the cryo chiller working nicely. We've got the cold side going to -40 and sustaining. I've also put in this heat exchanger that is going to be connected to the heat pump that heats up the fluid before it goes into the turbine. And I'm going to do some work on that heat pump now to make it more efficient. I'm going to show you some of those tricks. Now, what we've got here is a compressor for a 5 kilowatt heat pump. That's 5 kilowatts output. It only takes in 1 kilowatt of electricity to run it. But because it has a COP, or a coefficient of performance, of 5, you put in 1 kilowatt of electricity and 5 kilowatts of heat energy is moved to the storage bank. We are going to install the 5 kilowatt heat pump compressor into the 11 kilowatt heat pump shell, because it has the 11 kilowatt fincoil at the back to capture heat energy. We also have the 11 kilowatt heat exchanger, which exchanges the heat energy from the refrigerant gas to the water. And we have the circulation pump that comes with this machine. And the reason why we need to use this equipment with a 5 kilowatt compressor is because we're going to install a regenerator. And the regenerator, I'm going to show you how that works now. How a normal heat pump works is the compressor will compress the refrigerant and it'll get very hot, like 80 degrees Celsius. Then it'll go to a heat exchanger, which exchanges the heat to the water in the tank that we're trying to heat. And then the desaturated but still high pressure gas goes across to the expansion valve, which expands, and the low pressure gas becomes very cold. It then picks up heat energy from the atmosphere, and then it returns after it's warmed up and back to the compressor. But the issue here is that if I'm heating my water to 55 degrees Celsius, then I can't get colder than 55 degrees Celsius out here. So this pipe is still 55 degrees Celsius. And if my heat source is the air outside at 15 degrees Celsius, then the gas returning cannot be hotter than 12 or 14 degrees Celsius. But so we've got hot here that's being wasted and cold is going into the compressor. So an easy fix to do is just to put in a regenerator heat exchanger. What that allows us to do is, after the compressed gas has finished here and it's still hot, it goes through a heat exchanger but maintains its pressure, and a lot of the heat energy is transferred to this pipe at the bottom here. So then you'll have 55 degrees Celsius going in here. You'll have about 30 or 35 degrees Celsius coming across here. The rest of it has gone across. And then you have 12 degrees Celsius going in and about 30 degrees Celsius going back to the compressor, which can make a heat pump up to 20% more efficient. But here's the issue that I have with this as well. If I have a 5 kilowatt heat pump and I put a heat exchanger into it, it could be now a 6 or a 7 kilowatt heat pump, but it's still running on a 5 kilowatt coil and a 5 kilowatt heat exchanger here. So now what I'm doing is I'm putting a 5 kilowatt compressor into an 11 kilowatt machine shell with an 11 kilowatt fincoil and an 11 kilowatt heat exchanger and an 11 kilowatt heat pump's circulation pump, which can circulate a lot more water and faster, so that I can take full advantage of putting in my regenerator heat exchanger. So that is why I am putting in a 5 kilowatt heat pump's compressor into an 11 kilowatt heat pump's shell with the fincoil and the heat exchanger and the circulation pump, is so that I can make full advantage of the regenerator heat exchanger, which I've built over here, which is going to go into this machine with the smaller compressor. The smaller compressor will use a lot less electricity, and it will also, with all of the upgrades I'm doing, it's going to output a lot more heat energy than it would normally do, because it has better infrastructure around it. Yes, it's more expensive, but the point of my exercise is as much efficiency as I can get. The reason why I need so much efficiency is because the aim of what I'm trying to do here with the Tesla turbine as well and the cryochiller is to generate a positive amount of electrical energy using only heat energy from the atmosphere. So we're going to harvest heat energy from the atmosphere and generate electricity using that through an organic Rankine cycle generator. We are also going to cut out this three-way valve or four-way valve, which allows us to reverse the flow. The reason why we're going to take it out is because the hot refrigerant that we're trying to use to heat something up is going through this metal device right next to the coldest cold side, and what happens is it leaches away our advantage and it makes the hot that we want to use cold, which is a big inefficiency. So I'm going to bypass it since we're not going to reverse the machine and it's just experimental, but I'm going to take this out and we're going to run the machine without the reversing valve. Woo. We've finished brazing all the parts together. Now we're going to pressurize the heat pump to 5 bar and then go over all of the joints with soapy water to see if we've got any leaks. I've checked all of the brazing that I've done with some soapy water under pressure. There doesn't seem to be any leaks. So now I'm going to remove the pressure, and then I'm going to put on a vacuum and vacuum all of the cavities out to get all the moisture out of the system and all the oxygen. And then after that, we will gas it again.